This videotape is designed to acquaint not only new F-16 pilots, but also the experienced pilots with the F-16's departure and deep stall characteristics. Additionally, we hope that throughout this film you will be exposed to techniques for the optimum employment of the F-16 and techniques that should prove valuable should you encounter an out-of-control situation. We've organized a cross-section of video sequences to accurately portray the various departure and deep stall characteristics of the F-16. We'll give you some insight into proper techniques for optimum recovery from high pitch attitude, low airspeed situations. Finally, we'll discuss proper recovery techniques should you experience a departure or a deep stall. Before we begin these sequences, a quick review of the flight control characteristics of the F-16 is essential. As you know, the F-16 has relaxed static stability, which aids in maneuvering potential. Because of this relaxed stability, the F-16 flight control system was designed to give good handling qualities and at the same time attempt to extract the maximum turn and roll performance possible from the aircraft. The flight control system limiters are designed to safely permit the pilot to maneuver close to the departure boundaries with very little concern. However, these limiters can be defeated. In some cases, the defeat of these limiters leads to departures and deep stalls. Let's look at the major flight control system limiter. The available angle of attack is a function of G loading. At 1G, approximately 25 degrees angle of attack are available. Abrupt aft stick inputs generally lead to a slight overshoot of the AOA limiter into this regime. This overshoot is actually designed into the aircraft to provide a good nose pointing capability. However, if this abrupt aft stick input occurs at a very low airspeed, particularly with the aircraft at the aft center of gravity, it's possible to greatly exceed the 25 degree limiter into the 29 degree regime. When the AOA exceeds 29 degrees, the flight control system will use rudder, flaperons, and horizontal stabilizers to oppose any prevailing yaw rate. Let's use our model to help illustrate this point. The flight control system deflects the rudders to oppose a yaw rate, and also the flaperon and horizontal tail to roll the aircraft into a yaw rate. This anti-spin flight control input can lead to departures, but why have a yaw rate limiter that can lead to the aircraft departure? The answer is that the F-16 has a fast, flat, and maybe an unrecoverable spin mode. The yaw rate limiter works during upright deep stalls to counter this spin mode. The bottom line to prevent overshooting the AOA G limiter is to maneuver the aircraft smoothly at low speeds. Two other limiters are the roll rate limiter and the rudder limiter. The roll rate limiter limits the maximum roll rate to 228 degrees per second and reduces this rate as a function of angle of attack, airspeed, and the available horizontal tail. The rudder limiter reduces the amount of rudder the pilot can command as a function of roll rate and angle of attack. Essentially, all the limiters are helping to prevent undesirable flying qualities to provide the maximum maneuvering potential to you, the pilot. The next important feature of the F-16 is a manual pitch override switch. Above 25 degrees angle of attack, the flight control system overrides the pilot inputs to the horizontal tail. Above 29 degrees angle of attack, flaperons and rudder are automatically deflected to prevent spin entry. Additionally, one horizontal tail is moved up to a maximum of 10 degrees from a full trailing edge down position to oppose any yaw rate. The MPO switch is used to allow you to gain partial command of the horizontal tail position. Yaw rate limiting is still active and will continue to command the tails to move differentially to counter this yaw rate. Once you have engaged the MPO, and assuming for a moment that no yaw rate exists, the tails will position themselves symmetrically according to stick position. Therefore, if the MPO switch is engaged and the stick is full forward, the tail will be in the same position as before MPO engagement. Pitch rocking is initiated by observing and reinforcing any natural aircraft pitching motion. More about correct pitch rocking later. With the MPO engaged, the rudder command is still active from the rudder pedals and will add or subtract from the yaw rate limiter rudder input. During inverted departures, the flaperons and rudder are still available to the pilot. However, the horizontal tail will be fully deflected to oppose negative angle of attack. The flight control system does not provide anti-spin control inputs during inverted departures, and should the aircraft establish itself in an inverted deep stall position it is necessary for you to counter any yaw rates with rudder inputs before attempting to initiate an MPO recovery. The roll axis is still active but should not be used. Attempting to roll the aircraft upright will not be effective and will actually result in more yaw rate. There are generally three departures common to the F-16. The first is a high pitch attitude departure. Essentially, the pilot runs the aircraft out of airspeed in a nose-high attitude. As the airspeed decreases and the aircraft falls downward, the AOA rapidly increases. Generally, this departure will lead to a self-recovery unless the initial pitch attitude is 55 to 70 degrees nose-high. In this case, the nose-down pitch motion as the nose falls may not be sufficient to recover the aircraft, and a deep stall may result. The departure is very smooth, and the pilot will only notice that he has departed by observing the AOA gauge pegged at 32 degrees. The inverted nose-high departure is identical to the upright departure. However, the AOA gauge will be pegged at -5 degrees. The second departure is a pitch rate departure. This departure occurs when the stick is abruptly pulled aft at low airspeed. The most likely scenario to have a pitch rate departure is during a nose-high recovery attempt where the pilot rapidly pulls the aft stick to get the nose moving. This generally leads to a departure characterized by a slight right roll to a wings level position, followed by either self-recovery or a deep stall. Two other departure types deserve mention. Although they are seen from time to time in flight tests, they are generally not a problem in the TAF. The first is the yaw rate departure. When loaded with external stores, the F-16's directional stability decreases. Particularly with asymmetric stores, left wing being worse, a rapid pull or rolling pull can lead to a yaw departure. Also, several departures of this type have been attributed to the asymmetric leading edge flap extension. Entry into this type of departure is relatively easy to recognize due to the lateral side forces present in the cockpit and the uncommanded aircraft motions. If the pilot feels this lateral side force and releases controls immediately, this departure usually leads to a half roll and recovery. If aft stick is held too long, the results can be dramatic. The last type of departure is a departure encountered during a prolonged roll. This type of departure can be experienced following a maximum command roll and is most likely while on the AOA G limiter. With certain pitch critical loadings and after exceeding the flight manual roll restrictions, the horizontal tails are unable to prevent an overshoot in angle of attack. If this overshoot exceeds 29 degrees, the commands of the yaw rate limiter may lead to a yaw departure. As in the erect departure, the departure will only be noticed on the angle of attack gauge until the yaw rate limiter is tripped. So how do we combine this knowledge of departures and the flight control system mechanization to prevent departures? The first key ingredient is to maintain situational awareness of the aircraft attitude and airspeed. The low speed warning horn is designed to help you in this area. As you know, the low speed horn is a function of pitch attitude and airspeed. It will generally give you a safe margin for recovery if you execute the proper procedures. However, three factors tend to complicate the departure situation. First, the design of the F-16 gives great visibility with less than abundant cockpit cues as the aircraft pitch attitude or airspeed. Second, 30-degree seat tilt makes it difficult to determine attitude when you're near the vertical. And third, if you have any angle of attack on the aircraft, the pitch attitude and the flight path angle do not coincide. In fact, they may be 25 degrees or more apart. Since the pilot has no idea where his flight path is located until he unloads, it's imperative that the first step in a nose-high recovery be to unload and determine the proper direction for recovery. Once you've unloaded, then the pitch attitude of the aircraft is a reliable recovery tool. The ADI will be accurate, or you can look outside for references. Keep in mind that the pitch ladders in the HUD are inaccurate above 60 degrees of pitch, or for that matter, dive. So roll the quickest direction to the horizon, smoothly blend in aft stick, and watch the nose. I don't suggest full aft stick in this situation. Remember, the aircraft will be attempting to follow your aft stick commands. If you pull rapidly to the limiter, the possibility of an overshoot and departure are high. Just pull aft enough to start the nose tracking toward the horizon. Now comes another critical point as the nose nears the horizon. Don't be tempted to roll out at a low airspeed. If you try this, it's likely you'll be at or near the AOA limiter, and by rolling, you may end up assaulting both the roll and AOA limiters. This could also lead to a departure. Let the nose drop. I suggest at least 45 degrees nose low, if practical, and smoothly fly the aircraft until airspeed increases to 200 knots. When you reach 200 knots, then roll out and recover. But where do most departures occur? Probably the first and most common is the nose-high roll reversal. Generally, this occurs during an early defensive BFM engagement.
Jump.
The F-16 has a great thrust to weight ratio, but when it's pulling G's and going uphill, it slows down quickly. Since it also lacks airspeed cues, the situation is ideal for an F-16 pilot to lose SA of his airspeed as he looks over his shoulder during a defensive setup. As he continues his hard turn uphill, if the Bandit overshoots, or for that matter goes lag, the pilot is often required to reverse to either force the overshoot or maintain sight. Since he wants to force the situation quickly, this reversal is generally a loaded reversal. Airspeed is now low, the nose is high, and the low speed horn comes on. The pilot must transition from looking over the shoulder, recognize his pitch roll attitude, and recover, all the while he's losing valuable airspeed. The next most common scenario is similar to the first in that the pilot finds himself in a nose-high, low airspeed arena. However, the departure occurs when the stick is abruptly pull full aft.
Roll, stop, pull. There's 32, releasing the controls.
Note that the abruptness of the stick inputs to generate a departure is a function of the airspeed, i.e., the lower the airspeed, the slower the input that will result in a departure. Initially, the pilot will see a very high pitch rate. However, as the AOA rapidly exceeds 25 degrees, the nose movement will stop or even reverse, and the aircraft has departed. Another problem comes when the pilot assaults two limiters. This occurs when the pilot is rolling and pulls full aft stick, or when you're pulling full aft stick begins a roll. Probably the most common arena for the two limiter assault is during a scissors or during a lead turn out of the vertical. In these situations, the pilot is rolling the lift vector and applying aft stick at a relatively low airspeed. To improve your chances in this arena, attempt to minimize inputs in one axis before making a large input in the other axis. Or, in simpler terms, if you need to roll, hold the aft stick constant, and likewise, if you need to pull, hold the roll input constant. Another, less common departure is a yaw departure. This is less common since most air-to-air loadings don't have a directional stability problem. However, when you add centerline stores, the directional stability decreases. When you add asymmetric missiles, particularly on the left wing, the stability decreases. And finally, as altitude increases, the directional stability decreases. Add these three up, and you get the scenario for departure. Take an asymmetric missile, centerline tank loading to 35,000 feet, and maneuvers you could safely accomplish at 15,000 feet may now lead to a departure. The most common of these situations is a hard pull followed by a hard left roll. If you're quick, you'll feel lateral acceleration, you're sliding sideways in the cockpit, at the initial roll input. Or maybe you'll see a quick reduction or hesitation in roll after 45 degrees of roll. If not, you'll definitely notice the snap roll type maneuver that follows. Generally, if you release a stick when you feel the lateral acceleration, you'll stop the departure and at most will get a half roll in the opposite direction. If you wait for the roll rate to stop, you'll generally snap roll for a full 360 degrees and may enter an erect deep stall. If you wait for departure, it will be extremely disorienting as the aircraft reverses direction and rapidly rolls uncontrollably until the airspeed decays. So now that you've learned all the bad things you can do with the jet, how can you go out next time, employ to the maximum extent possible and not fear departures? Well, first and most important is to maintain awareness of your pitch attitude and airspeed. Even looking over your shoulder, you should have a good idea of how high the nose is. Additionally, if you're pulling near the limiter, buffet is a good indication. Remember your true flight path, the one you would see if you were to unload, is lagging your pitch attitude. Airspeed awareness is something that's hard to learn and easy to forget. Know your entry airspeed before going into the vertical. Develop a feel for how hard and how long you can pull before reaching a relatively low airspeed. Initially, you'll have to risk losing sight of the bogey, and actually check the airspeed indicator more often. If you start up purely in the vertical, 250 knots in afterburner is a good number for a clean jet. If you don't have this airspeed or are dirty, then make the maneuver in the oblique. Watch the tendency to reverse the turn direction once you're in the vertical. And when the horn comes on, knock off what you're doing and execute the proper recovery. Don't panic and do a rolling pull down. If during any maneuvering you feel a side force in the cockpit or the aircraft reverses direction without command, release the stick and observe the nose position and response. Until you've experienced several of these deep stalls, it's hard to tell exactly when you pass the point of departure and have entered a deep stall. Generally, the departure may be very benign and only indicated by the AOA gauge being pegged at 32 or -5. Your first hint that you're in a deep stall is when the nose stays near the horizon, about plus or minus 30 degrees, and the aircraft doesn't recover. Keep in mind that the nose will probably not be parked exactly on the horizon. Depending on the amount of energy and the external configuration the aircraft had at its initial deep stall entry, the nose could be either extremely stable with no pitch rates, or it can be extremely oscillatory in both pitch and roll. After seeing lots of deep stalls here at Edwards, we feel we're in a deep stall when the nose reverses away from the ground. At this point, if the pitch oscillations are high enough, there's a good probability of a self-recovery. However, if the aircraft is stable, or if it develops a lot of side slip, generally this is to the left, as the nose drops, there's a high probability the pilot must pitch rock out of the situation. Is it important that you immediately recognize that you're in a deep stall? Well, that all depends on your altitude. If you don't recognize a deep stall until several oscillations have occurred, it won't hurt as long as sufficient altitude remains for recovery. During this time, the AOA gauge is probably the most reliable indicator of a continued out-of-control situation. It will generally remain pegged if you're in a deep stall. There are only 3 deep stall modes. The first is the erect non-oscillatory. In this mode, the nose is close to the horizon, very little pitch oscillation is present, and the pilot experiences a very smooth ride. The aircraft may be yawing to the left or right. The erect oscillatory deep stall is a result of external stores or entering the deep stall with a lot of energy. Generally, a clean airplane will dampen to a non-oscillatory deep stall after a few pitch oscillations. The oscillatory deep stall can be particularly disorienting due to the high rates of pitch, roll, and yaw at the same time. Even though it appears the aircraft should recover as the nose pitches down, the presence of large side slip will couple in the angle of attack at the nose low position, and the aircraft will remain in a deep stall. The inverted deep stall is generally more stable than the upright deep stalls. Characteristics are not as dependent on configuration, since the high negative angle of attack masks any airflow over the bottom of the aircraft. This deep stall is very disorienting the first few times. Additionally, if your seat belt is not tight or if you haven't lowered your seat, it may be impossible to reach the MPO switch. Pitching motions are usually small, and again, some yaw rate may be present. If any pitch motions are present, the aircraft may rock itself into an erect deep stall. This transition is generally fast and disorienting. So when and how do you recover from deep stalls? The caps have been developed to help recover from deep stalls, but even if you recall them correctly, you may still need some more knowledge to successfully recover. First, if you run the aircraft out of airspeed or experience an uncommanded motion or high side forces, release the stick. Watch the nose motions, the AOA gauge, and retard the throttle to mill if you're in AB. During this time, you may experience several other unusual characteristics. First, the engine may stall or stagnate. Forget about the engine until the aircraft is recovered. The probability of an air start during a deep stall is extremely low. Additionally, if the engine were shut down and the EPU failed to function, you wouldn't have hydraulics to power the flight controls for recovery. With the engine stalling or stagnating, at least it will have enough RPM to drive the hydraulic pumps. Second, you'll probably light up most of the flight control lights. It's not unusual to get a dual FC fail, hydraulic oil pressure, ADC, CADC, leading edge flaps, flight control system, or servo lights. Ignore all of this and concentrate on recovery. It may also concern you that all these lights generally illuminate just as the yaw rate limiter slams the horizontal tail into a stop with a loud bang. Don't worry, the flight controls are still working properly. So the bottom line is that if you depart, expect noises, lights, and whistles. These are normal out-of-control characteristics and no pilot actions are required. So now we're watching the nose motions in the AOA gauge. If the gauge is pegged, you've departed. The aircraft will more often than not self-recover from this point. If it pitches down vertically, come on the stick and try to keep the nose vertical until you've reached 200 knots. If the AOA gauge stays pegged, and if the nose is pitching around the horizon, you're in a deep stall. Remember, the amount of pitching moment you get with the MPO engage may be small compared to the natural pitching motions of the aircraft. So curl your index finger around the MPO guard and engage the MPO with your thumb. Make sure that when you engage the MPO, you're doing something with the stick. If not, the tail will just streamline and delay any recovery. So watch the nose. When it reverses direction, engage the MPO and push or pull to reinforce the nose movement. Do not reverse the stick input until the nose motion reverses. Blindly pulling the stick when the nose is going down may destroy any natural pitching motion and prevent recovery. Additionally, rapid cycling of the stick or anticipating the reversal of the stick will not be effective. Generally, if the nose pitches to minus 45 degrees and hesitates, it will probably recover if you keep holding the stick in the recovery direction. If not, the nose position will reverse and another pitch cycle will be required. Let's concentrate on the erect deep stall first. If the nose reverses upward, then pull back until it reverses downward again. The most important things to do are 1. Reinforce any natural pitch oscillations from the start, and 2. Wait until the nose has reversed direction before you reverse the stick. Don't get anxious. Concentrate on these procedures and they'll work every time. In the extremely rare occurrence where there are no initial pitch motions, then pull away from the ground until the nose reverses. In this case, you may not get any initial nose movement. If not, then the nose may not reverse downward. Only in this case will you hold the stick aft for several seconds, 3 to 4, then reverse. This reversal will result in a nose down pitch motion, and from now on reinforce this motion each time the nose reverses. When the stall breaks, the nose will rapidly pitch downward as it breaks the angle of attack. Additionally, the aircraft almost always shudders just as the stall is breaking.
40,000 feet, 41,000.
Okay, Air's going to 30.
32.
32.
We're departed. You can feel the yaw rate limiter kicking one way or the other.
Okay.
Caution. Caution.
Okay, would you say we're in a deep stall there?
Yeah.
Okay, why don't you recover?
Okay, I have the aircraft. Okay, up. Down.
That's good.
Okay. Is okay to recover?
3-2, ready to recovery.
Nose is falling, sticks full aft.
Departure.
Off the controls, ADC light is on.
Caution. Caution.
Ooh, good one.
Warning, warning. Warning, warning.
Up. Down and holding. Up. Down. Come on out, babe. Come on out. Up. Down. Up. Down. Come on. Down. This is crazy. Down. Up. Down. Come on, fly, babe. Down.
That's 25.
Down.
Deploy.
If you don't try to keep the nose stabilized in a diving attitude, it may tuck under to an inverted deep stall. So fly it smoothly into the vertical. If it does tuck, wait for a recognizable inverted deep stall, then start the pitch rocking all over again. Which brings us to the inverted deep stall. Of course, the pitch rocking must reinforce the natural pitching motions, which are typically less in an inverted deep stall, but it's important to stop any yaw rate. I don't particularly recommend looking at the turn needle. First, it's not something we're in the habit of using in the F-16, and second, it's easier to just look outside and do the natural thing with your feet. If the nose is yawing left, then press the right rudder until it stops. If it's yawing right, use the left rudder. Stopping the yaw rate will greatly help any pitch rocking and may actually recover the aircraft at that time. If you can't determine the yaw rate by outside references, then rudder opposite the turn needle will work. Of course, if there are no pitch motions at all, the first maneuver should be a push. Then just as in an erect deep stall, reinforce any pitching motions by reversing direction after the nose reverses. It's very easy to transition from an inverted deep stall to an erect deep stall during the recovery. To prevent this, aggressively fight to hold the aircraft vertical until 200 knots.
Going through is -5 alpha, and there's departure, putting my hand down.
Caution. Caution.
Nose is coming down. A little bit of yaw rate to the right. Okay. I'm stopping it with left rudder. I've got the aircraft pushing, pulling, pushing, pulling.
Warning, 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 warning.
I'm going to recover it.
So let's try to summarize all this and tie it to the caps. First, if you depart or the aircraft has uncommanded motions or side slip, release the controls and observe. If the throttle is in AB, retard it to mill. If you find yourself hanging from the seatbelt in an inverted position, rudder opposite the turn rate. If you determine that the nose is stable or oscillating about the horizon and the AOA is pegged, MPO override and hold while you're cycling in phase with the prevailing aircraft motions, and remember, reversing only after the nose reverses. Finally, as the nose pitches over for the recovery, fly the aircraft to a near vertical attitude. In summary, the most important guide to preventing departures in the F-16 is to have a good understanding of how the flight control system works and to maintain situational awareness of when you're approaching one of these limits. The subtlety of the airspeed and attitude cues in the F-16 require the pilot to devote more time during an engagement on keeping up with trends in these parameters. If you find yourself approaching these limits, maneuver smoothly and avoid the tendency to assault two limiters trying to rush the recovery. If you do depart, release the controls, observe what's happening to the aircraft, and note your altitude. If you find yourself in a deep stall, reinforce the natural aircraft pitching motions and remember not to reverse until the pitch attitude reverses. Finally, fly the aircraft to the vertical until 200 knots. Remember, also, 10,000 feet is a mandatory ejection altitude. Don't press. And if you're low on altitude and energy during engagement, don't press your luck. Most out-of-control F-16 accidents began with a departure just above 10,000 feet, and the pilot didn't even have a shot at recovery.